Okay, good afternoon. I think we're going to get started. There may be a few more folks coming in, and they're welcome to sit down wherever. My name is John Dickert. I work for Continental VDO. We manufacture OE tire pressure sensors and also aftermarket, the Ready sensors. I'll spend a little time this afternoon talking about Ready sensors and tire pressure monitoring in general. I want to try and give you a flavor of how this thing works, how the system works.
Is there a brochure, book or something?
There's brochures back on the table.
Are you going to reference them?
There's nothing during the presentation to reference. It's all on the screen.
Okay,
All right. The agenda for today, we're going to do an overview of TPMS, the components, how the system learns, localization. I'll talk about the mechanical overview, electrical overview, communications and protocols. There's the different product types. We have clamp-in, snap-in, and banded sensors. Spend some time on aftermarket opportunities. We'll talk about the failure modes, what to look for. Installation, some scanning tools. There's some tire pressure basics in here that I have mainly for the VOTEC students. We'll probably skip over that a little bit. I think most of you folks know a little bit about the tire pressure basics. Talk about some current regulations and the universal and multi-application TPMS. There were two methods used for TPMS, indirect and direct. In the beginning, 2001, somewhere around there, they started with indirect and they used the ABS system. Then we moved more of the manufacturers moved to the direct system. Indirect, of course, it was very inexpensive. They already had ABS, but it was not exact because it used the wheel speed. The theory was if your tire lost pressure, it would spin faster, and that would signal a trigger that you have something wrong with your air pressure. But it really wasn't accurate, certainly wasn't as safe. So we moved more toward the direct system.
Do they still do that at all? The indirect at all?
They're still indirect on the road. Yeah.
They don't make it like
We're not manufacturing it anymore, no. So the way it works in the factory, the manufacturers start with a display unit. They have a receiver in the vehicle somewhere and then sensors mounted somewhere in the tires. And this one happens to be a banded. Most of them now, though, are direct. They're right on the valve stem. For Chryslers, Hyundais, Mercedes, Jaguar, other manufacturers, they have LF triggers up in the fender well. What this does is it triggers the sensor as it's in motion. That's how you get it to be in the auto learn mode. Instead of having to relearn each tire, you just put them in and drive it. And these triggers will activate them. Low frequency. It's a little slide showing you where they might be mounted up in the fender wells. There's usually only 3 of them.
Why would there be only 3?
I'll get to that. This is a good group. I've never had this many questions before. As the vehicle comes down the assembly line, there's some antennas, low frequency antennas, that are triggering the sensors, and that's sending a signal to the plant receiver. And it's collecting the IDs for that sensor and then written to the vehicle. But now that you're out in the field or at a service center or in one of your shops, there's different ways to learn the new identifiers. You'll need some sort of a communication tool. I have some scan tools back there on the table that I brought along with me. I have some examples also on a slide. You'll need some sort of scan tool. Some OE procedures tell you to deflate or inflate the tire once the vehicle's in the learn mode. Some of the earlier Fords, you had a round magnet, donut magnet, that you slipped over top of the valve stem. That would trigger it also. But the learning of a TPMS sensor always requires some sort of human intervention. If you change the pressure, you need to, somebody has to be involved to activate this sensor. The only solution we have right now is with the Chryslers and Mercedes with the auto relearn. They have the triggers up in the fender well. And I think
Just rotate the tires and drive it.
you can rotate the tires, you can do anything you want. It'll learn where they are. So far, well, no, I lie, because Volvo has it. Infiniti, Land Rover, Jaguar. I got to, yeah, I got to validate our corporate, our warehouse is in Allentown. So we have the warehouse for the entire United States. And I get the opportunity to validate some cars every once in a while. And I had a 2013 Jaguar, which was pretty nice. And that auto learned within a quarter of a mile.
Well, if you ever replace a sensor in the Chrysler, you don't have to program the ID in, it'll identify it.
It'll do it automatically. Put it in the wheel and drive it.
Does it have to match the other three?
No.
No.
No. I'll get into this later. There's three things the vehicle needs to see. It needs to see the right frequency, it needs to see the right protocol, and it needs to see the ID number. Once it sees those three things, it knows that that sensor belongs to that vehicle. I had one up here. It's back there. That sensor will belong to that vehicle and not one of the others. So each sensor has a unique ID. It also has the correct frequency and the correct protocol inside that the receiver's listening for. For the Chrysler, if more than one sensor is replaced in a vehicle, the location of the new sensor identifiers are randomly distributed wherever that location happens to be. The automatic learning of an ID allows any new ID to be learned into the receiver of the vehicle. It's activated every time the vehicle has been parked for more than a certain period of time. In particular, Mazdas, which have an auto relearn, once the sensors are replaced, you turn the key on and off, wait for 15 minutes. Puts the receiver in the learn mode, and then you can drive it, and it'll relearn.
Now, if you don't do that and just drove it?
The light's going to be flashing.
Okay, you have to do the procedure.
Yeah. Because if you have it in your shop, you back it out, and the customer drives away with it, it's never going to relearn. You have to sit for 15 minutes. It's usually in the owner's manual, it'll tell you to do that. Ford has one of the more difficult relearn, to get it into the relearn mode. You press and release the brake pedal. Key on, on, staying on. Press and release the brake pedal again. Turn the ignition off. Switch it to on 3 more times, ending in on. You'll get a double horn chirp. Now that's ready to listen, you go around with a scan tool and trigger each sensor, and the vehicle's relearned. GM, we were talking about this earlier. GM, on the key fob, if you press and hold the lock and unlock button, you'll get a horn chirp. Now it's in relearn. Sometimes you might have to go to the DIC. Maybe there's a menu button on the shift lever or wherever, turn signal, wherever you have to do to get it into the learn mode. Again, that procedure is written in the owner's manual. We work in conjunction with TIA. They make a wonderful little book that I use religiously because I'm taking phone calls from all over the country. And I never know what vehicle I'm going to get hit with. So this has all the domestic vehicles written in here, alphabetical order, tells you what the relearn procedure is. And in the back of the section, it outlines each relearn procedure for every vehicle. If you turn it around, it's in red. Now you have all the imports, and it works the same way. This information is also in the Mitchell catalog, and it's in the owner's manual. We just found out that this book sells for about $180.
Who sells that?
TIA. It's a great book. It's a great tool because it lists everything. There'll be a video about it. But if you can get the same information off the owner's manual, I don't know. Yeah. Yes, yes. I have a short 10-minute video on how to identify a vehicle if it has TPMS. Can everybody see this screen? Okay.
On November 1st, 2000, Congress passed the Transportation Recall Enhancement, Accountability, and Documentation Act, or TREAD Act, which requires vehicle and equipment manufacturers to regularly communicate with the National Highway Traffic Safety Administration, or NHTSA, to identify the existence of potential safety defects and to advise NHTSA of foreign safety recalls and other safety campaigns. In addition to those requirements, the Department of Transportation was charged with updating the Federal Motor Vehicle Safety Standards, or FMVSS, to include a system in new vehicles that would warn drivers when a tire is significantly underinflated. After years of public comments, NHTSA released FMVSS 571.138 on April 8, 2005. And the timetable for every vehicle to include a tire pressure monitoring system, or TPMS, was put into place. Just over 2 years later, on September 1, 2007, the phase-in period was over. So from that point forward, every passenger car, multi-purpose passenger vehicle, truck, and bus manufactured for sale in the United States with a GVWR of 10,000 pounds, or 4,536 kilograms or less, must include a system to detect any tire with less than 25% of the placard pressure and warn the driver with a low tire pressure telltale on the instrument panel. According to FMVSS 571.101, the standard low tire pressure telltale is a yellow tire with an exclamation point in the middle. If technicians see this light during the bulb check when the ignition is turned to the on position or to a position between on and start, then the vehicle has a TPMS. If the TPMS telltale is no longer illuminated after the bulb check is complete, then the technician can assume that none of the tires are below 25% of the placard pressure and the tires are being monitored. If the telltale stays illuminated after the bulb check cycle is complete and the engine is running, then the vehicle has at least one tire below 25% of the placard pressure, or the TPMS may require a relearn procedure. However, if the TPMS telltale continues to blink for at least 60 seconds but no more than 90 seconds immediately after the bulb check is complete and then remains illuminated, the TPMS on the vehicle has a malfunction. Also known as a malfunction indicator lamp, or MIL, this telltale is a warning that the TPMS is not operational and therefore the tires are not being monitored. The MIL can also be identified by the letters TPMS in yellow that will remain illuminated when the engine is running. If a technician identifies an MIL after the ignition cycle, the customer should be notified immediately that the TPMS has a malfunction before the vehicle is moved or any of the tires are serviced. Besides using the yellow telltale or other displays on the instrument panel to identify a vehicle with a tire pressure monitoring system, technicians can also check the valve stem to determine if a sensor is part of the assembly. Most vehicles utilize a direct TPMS that consists of an electronic control unit, or ECU, that serves as the receiver for radio frequency, or RF signals from the sensors inside each of the tires. This allows the onboard computer to directly monitor the inflation pressure inside each tire and warn the driver when any tire drops below the 25% threshold. The most common sensors are part of the valve stem assembly, and they are divided into two main categories, clamp-in and snap-in. Clamp-in sensors are most easily identified by the large aluminum hex nut on the outside of a valve stem on each tire, and may or may not include the spare. While they are available in a number of different styles, the most common is the fixed angle sensor, where the valve stem does not move. Adjustable angle clamp-in sensors have a movable valve stem that is able to accommodate different valve hole profiles on original equipment and aftermarket rims. Clamp-in sensors can be a one-piece design where the valve stem and sensor are a single assembly, or a two-piece design, where the valve stem is one assembly and the sensor is another. On a two-piece clamp-in assembly, the sensor and valve stem are attached by a special bolt that has a specified torque setting. Likewise, the torque settings and hex nut size for the large aluminum hex nut that mechanically locks both the one-piece and two-piece sensor to the rim varies from manufacturer to manufacturer. Installation torque can range from 35 to 80 to 140 inch-pounds, but the most common hex nut sizes are 11 or 12 millimeters. When the hex nut is new, the threads are coated with a special anti-corrosive compound that is designed to prevent it from seizing on the valve stem. Since that coating is gone after a hex nut is removed from a valve stem, technicians should never reuse hex nuts when installing clamp-in sensors. In order to create an airtight seal between the rim and the valve stem, clamp-in sensors use a rubber grommet or O-ring that is specifically designed for the rim. While some grommets or O-rings may appear to have the same physical dimensions, the rubber compound may vary depending on the application and manufacturer. Therefore, technicians should always use the specified rubber grommet or O-ring for each particular sensor and rim combination. It's also important to note that after a clamp-in sensor is installed, the grommet or O-ring will begin to develop set dimensions that eventually become permanent. For that reason, grommets and O-rings should never be reused. Snap-in sensors are two-piece assemblies that utilize a special rubber snap-in valve stem that includes a brass post where the sensor can be attached on the inside of the tire. In order to easily differentiate a snap-in sensor from a standard rubber snap-in valve stem, the manufacturer designed special beveled edges just below the threads for the much larger valve cap. While there are definite physical differences between the two types of rubber snap-in stems, they are mainly cosmetic, so they can be interchanged. A small Torx bolt is used to attach the sensor to the bottom of the brass post on the special rubber snap-in valve stem. The installation torque for the Torx bolt is 11.5 inch-pounds, so the best practice is to use a torque device that is preset for rubber snap-in valve stem sensors. The other type of direct TPMS sensor is mounted to a band that wraps around the drop center well of the rim. Band-mounted sensors are most commonly found on 2006 to 2010 Ford, Lincoln, and Mercury vehicles, where the tires will have standard rubber snap-in valve stems, but the dashboard will indicate the vehicle has a TPMS. Since the band-mounted sensor is supposed to be installed opposite the valve stem, technicians can also use an electronic relearn tool to identify a tire with a TPMS sensor without removing the tire from the rim. In most cases, the rim will be stamped "Sensor may be inside." However, there are aftermarket retrofit kits that use a band and special cradle to secure the valve stem sensor to the drop center on the rim. These assemblies cannot be identified by the valve stem or the stamp on the rim, so technicians will need a relearn tool to identify a sensor on the vehicle. Likewise, there are chrome valve stems that allow for the attachment of a valve stem sensor, so the same limits apply when identifying an assembly with a TPMS sensor. All direct TPMS sensors must have a port where the air pressure can enter the sensor. On most valve stem and band-mounted sensors, the port is a small hole on the front of the sensor. The port may also be on the back side and include a small filter. Regardless of the position, the port allows the compressed air inside the tire to pressurize a diaphragm inside the sensor that ultimately determines if the inflation pressure is 25% below the placard value. Therefore, technicians should always inspect the port to ensure it is not blocked. When cleaning the port, do not allow any sharp or pointed objects to puncture the diaphragm and destroy the sensor. Since early indirect TPMS technology cannot comply with FMVSS 571.138, it ceased to exist with the 2008 model year. But there are still hundreds of thousands of vehicles with this system still on the road. Since there were different telltales when TPMS was first introduced, technicians cannot identify an indirect system solely by the dashboard indicator. Besides the standard rubber snap-in valve stems, indirect systems usually include a reset button somewhere on the dashboard. Technicians can also consult the owner's manual or other industry resources such as TIA's TPMS Relearn chart to determine if the telltale on the instrument panel is part of an indirect system.
In the factory, we talk about localization. Some automobiles have it on the dash where it shows you where the tire is and what the pressure is on the screen. Others just give you a light. No localization, usually used the basic models of GM and Ford, where they just activate each sensor, it transmits to the receiver, and you get a light. You don't know exactly which sensor is bad, but one of them is, or one of the tires is low, but you don't know which one. We also have front to rear. Pardon me?
Or a scan tool identify?
A scan tool would identify that, yes. Some cars have front to rear. A lot of pickup trucks have different tire pressures in the rear. Corvettes have different tire pressures. The way they do that is with two receivers. They have one in the front, one in the back. These two TPMS activate to the front receiver. It checks the pressure against those two thresholds. And the rear talks to another receiver, and it's based on the low frequency trigger that activates that sensor, and it sends a different function code than the others. So the receiver knows which ones are talking to it from the front and which ones are talking to it from the back. Full localization. You ask why there's 3 antennas. They usually use 3 antennas in these manufacturers. They localize the right rear, then they localize the left rear with an LF trigger, localize the right front, and sensor A never responds to a trigger, so they know where that one is, and that's full localization. They also do it with a dual accelerometer. RSSI stands for signal strength. I'm not sure what the R and the I are for, but it's the signal strength of the sensor itself. The blue line here represents the carrier wave that's transmitted from the sensor. When it's activated, the signal is displayed by this red line, which is right before the carrier on this side and right after the carrier. Whoops. Right after the carrier on the other side. Hit the wrong button. You see it right here, it's right after the carrier. And the signal strength from each one of those sensors is interpreted by the receiver. So
A battery or something inside that sensor?
there is a battery inside of it.
What's the life expectancy of that battery?
7 to 10 years. Don't get ahead of me. All right? So as this vehicle is driving through the assembly line, it's being programmed on where the sensors are and where they're placed within the vehicle. They also use a full localization with 2 LF antennas. It's a combination of how the sensor is triggered with LF or not triggered with LF and which side it's on. They also, some manufacturers use the keyless entry system, that receiver as well. If you have a vehicle where their keyless entry is not working correctly, chances are TPMS isn't either. You know.
Once you, if the battery goes dead in the remote as well, it will also kill the TPMS system.
Yeah,
You have to replace the battery in the little hand remote, and then you can put the car back into relearn, and it will automatically relearn once
Right.
that key fob is powered back up.
Yeah, keyless entry and TPMS are part of the same receiver. In this instance, these 2 receivers are talking to this antenna. The 2 rears are talking to the other antenna. It's getting the localization, knowing where the signals are coming from, where that tire is located on the vehicle. Different product types. This is an example of the clamp-in. They have snap-in, works the same way, only it has a rubber valve stem. We're making these right now as original equipment. They'll be available aftermarket from us probably next year. And then Ford uses the banded sensor up till 2010. Anything beyond that is clamp-in now. Clamp-in looks like the one that's in the tire back there. There's the size of the battery. It takes up at least 1/3 of the sensor and the circuit board. Just an exploded view of what's inside of it.
So that's not replaceable?
What?
The battery.
Battery is not replaceable. Most stems are not replaceable. We've just come out with our new aftermarket one that does have a replaceable stem.
Where do you get those?
You can get them from Rick. Yep. Mm-hmm.
We're buying whole sensors, taking the stems off so we don't have to reline.
Some of them are. Some of the stems are not replaceable. I'll show you which ones. Just a mechanical drawing of how the clamping works. They talked about the grommets when you change the sensor, the parts kit. The housing, the valve, the antenna, these are all the chemical components, the chemical makeup of each one of the components. It's the type of brass alloy, the valve, the antenna, the makeup of each alloy. Every manufacturer is different. So their rubber grommets, their rubber O-rings may be made of different material. If you have this type of sensor, this is the TG1B. It has a little metal strap right here. That communicates with the sensor because the valve stem is part of the antenna. These cannot be changed. Even though it looks like you can easily do it, you can, well,
All you do is unscrew it, put it back on.
you can't legally do it. The FCC regulates how these things are able to transmit, and they will not allow us to replace those valve stems because it could interfere with the transmission.
Is that why we haven't been able to buy the valve stem?
You can't buy that valve stem.
That's exactly.
No, because
the one
it's,
I'm talking about. I think that's Chrysler.
yep, they're not replaceable legally.
Yeah, and I've taken it out of brand new sensors because not being able to.
Because if you screw up this little strap here, you're going to get a TPMS light. It's not going to communicate. Mounting procedure. This is off of the instruction sheet that comes with the sensor. It's very, very important to know that the hex nut has that anti-corrosive on it. So once that's changed, it's gone. Put a new nut on it.
That stuff isn't working.
It depends on the alloy that the stem's made out of. The OE Chryslers, I think, have an issue. Always spin them on hand tight before you put a wrench to it. Make sure you don't cross thread them. Again, this is just a snapshot of the instruction sheet on how to install them. This is part of the spare parts kit. Make sure every time you change a sensor, we recommend that these parts be changed even if you change the tire and don't touch the sensor. We recommend that you change the spare parts kit. The valve core is particularly important because it's nickel plated so that it doesn't corrode inside the valve stem. A cap is also part of it. Let's see. This is normal behavior, like you saw in the video. The washer and the seals are going to take a set to the rim. They cannot be reused. These are normally going to extrude somewhat as they take a set to the rim as well. That's normal. What's a little abnormal is if the fixed valve stems are not going to ride down against the drop center. The angled sensors, the angled valve stems will. We recommend that you have it down against the drop center. If you over torque it, you're going to snap the housing. If you try and replace these type of stems, you might ruin the strap for the communication. Like this, they broke the antennas. The light's definitely going to come on with that. If you cross thread it, you're going to damage the stem. And of course, if you over torque it, you're going to snap it right out of the housing. This is what's included in the spare parts kit. Banded sensors, pretty much the same. They're mounted 180 from the valve stem. It's just a matter of having the wheel in balance or help with the balancing. If you notice, there's some writing right here on that sensor. It's very important that what that says is that has to face the outside of the rim. Very important. The accelerometer inside there has to spin in a certain direction. So even though you do a relearn and the light goes out, customer will drive away and it's going to come back on because it doesn't see anything. Did you have a question?
I just have a suggestion. If you come across one of them sensors, you have to replace it, cut the band, throw the band away, put a regular stem sensor in it.
Yeah. These will replace.
They replace the band ones and they're 10 times better sensors.
Yeah.
They're
Again, the vehicle's looking for the right frequency, the right protocol, and an ID number. These have the same frequency and the same protocol as that sensor.
They're a lot cheaper.
Yeah, they are.
You're saying that has to face the outside of the wheel because of rotational direction?
Yes.
Does that mean you can't rotate the tires from left to right?
Yeah, because the outside of the rim is still going to be on the outside.
But the wheel will be turning in the opposite direction
Yeah.
when you change sides.
But the accelerometer will still go in the right direction. Even though as long as it's facing the outside of the rim, it'll work. But if it's the other way, it's not going to go. I know what you're saying, but it's the way it's positioned inside that sensor. It has to face the outside of the rim.
Okay. That's an easy way to get around not messing that up. Just cut it off, put one like you got.
Put one of these on. Yeah, yeah. This is the breakdown of what's involved. And there it says, locate this edge parallel to the outside rim. Snap in, like I said, we're making these for OE. The customers like this better. It's easier to work with. You just snap them in. It's less likely to corrode. And it works exactly the same way as the inside of it works exactly the same way as this one. So what's inside? It's an ASIC board, which is application-specific integrated circuit. And it's got lead frame. I'm not going to get into a lot of the unless somebody in here is an electrical engineer. I am not. But there's a lot of stuff packed inside of these things. There's a pressure and an acceleration chip and a Philips RISC processor. Pressure membrane that interprets the pressure of the tire. I'll explain more about interpretation. And then, again, the accelerometer. When the sensors aren't seeing any movement, they'll go to sleep to conserve battery life. The way it works with the pressure inlet, it pushes against this diaphragm, which activates these piezo resistors. The piezo resistors activate certain bits on the integrated circuit. It's not a pressure-to-pressure interpretation. When this activates bit 16 on a General Motors protocol, the receiver will interpret that as 32 psi. but bit 16 on a Ford protocol may be 20 psi. So you have to understand it's not pressure to pressure, it's an interpretation of which bit in the circuit is activated. In the accelerometer, as the centrifugal force moves this plate, it activates this resistor, lets the sensor know that it's in motion. More thought went into batteries than you can possibly imagine. It's a coin-type battery. They've chosen lithium manganese as the metal of choice for this. The lifetime says a minimum of 10 years. That's pretty much maximum. For 10 years that's pretty good. Here's the different components that were tested: lithium manganese, lithium carbon monofluoride, and lithium thionyl chloride, which I can't even pronounce. This one's the best, but it's very expensive. So we chose the lithium manganese because it's the top performer and the least expensive to use. Battery basics: you have an anode and a cathode. Chemical reaction produces electricity. And battery behavior is very simple. Application needs current. It drains it from the battery just like a water tank. You also have internal resistance, and that increases over time as the chemical reaction is taking place. So the aging effect is also going to lead to the power consumption. The engineers have found out that self-discharge is about 1% per year at 25 degrees Celsius. You also have the high temperature, which is also going to affect the battery life. It leads to permanent degradation of the internal resistance and can lead to the electrolyte leakage. Low temperature also. It affects the lead to a voltage bit set at low temperature, but it's cleared when the TPMS warms up. So the three major causes of battery life: regular consumption, extreme temperature, and aging. I mentioned this earlier. If there's anything at all that you get out of this class tonight, know the difference between frequency and protocol. These are advertised as being pre-programmed. They have the protocol inside, but they still, along with any other sensor, has to be relearned to the vehicle once it's put in, with the exception of Chrysler and those. We have 315 and 433 megahertz. Those are the two frequencies. GM is now coming out with 314.9 because 315 is the emergency channel in Japan. So they went to 314.9 for whatever vehicles are being exported to Japan. All these different things over here are the different ways the signal is transmitted to the receiver. It's the different forms of Morse code, if you will. That's the easiest way to explain it. And because there's so many different ones, it gets very confusing and complicated. On the LF side, the low frequency side, the receiver or the sensor sees a trigger that activates it. It sees something that it has to do something now. It has to transmit, and then it transmits the LF data to the receiver. All that protocol then, depending on the manufacturer and how they want to do it, comes out in either ASK or FSK modulation. ASK modulation, if you want to know the formula for that, again, not an electrical engineer. But the carrier wave is multiplied by the digital signal, and then that turns that signal into ones and zeros. FSK, frequency modulation, uses a different frequency for a 1 and a 0. PLL is an abbreviation for a phased lock loop, uses a crystal oscillator with a high stability for the reference frequency oscillator. I don't know what it means, I'll be honest with you, but it's in there. And it works. The FCC regulates these very heavily. They tell us how a device can communicate, how long it can communicate, how often, and what's the power. Because this isn't a constant frequency communication. It's only so many minutes. The FCC will not let this transmit continually. Another breakdown, a flow chart of from the battery where it goes through each part of the integrated circuit, through the process controller, and through the antenna. Failure modes. Most common causes is why you can't get a vehicle to relearn. I mentioned it before, heavy window tint. Somebody wants to really tint their windows up after they've got the car. The frequency or the transmission will not go through that window tint if it's real heavy. Anything metallic in the way, oh, is it this class or another? I'm talking about much larger wheels. It may have been too much metal in the way. I kind of doubt it, but it's possible. Differences in the warning telltale. You'll hear this again. If it flashes, you have a problem, a serious problem. If it's on steady, it's almost always air pressure. 25% threshold. This is programmed to go off 25% below the placard pressure. So if your OE wheel was 32 psi and you want to pimp out your ride and put a large wheel and a low profile tire on it that now has 50 psi in it, this sensor is not going to trigger till that's down to 24. It's 25% off the placard pressure. You cannot change that. You can change it in the receiver, but you can't change it on there. That protocol is in that circuit board and it won't change.
That sensor doesn't read over inflation?
The OEs do. Some of the OEs do.
I see.
Yes.
But some guy was 50 and it's supposed to be 32.
The way it works is that circuit board, there's only so much room on there. Our aftermarkets have all the different protocols in. The OE only needs one protocol. So it can put in high pressure. It can put in parking supervision. Parking supervision means it doesn't really have to be rolling. If the tire slowly goes down the parking lot and you turn the key on, you're going to see a light before you even roll away. We're coming out with that at the end of this year. It's going to be added to the circuit. Galvanic corrosion, dissimilar metals. Metal cap on an aluminum stem, going to eat it up. Brass core inside of here is going to eat it up. A lot of things that are going to cause these things to fail.
The cores that come in there, are they brass nickel plated?
Brass nickel plated. That's why it's important to torque them correctly. If you over torque them, you're going to scrape off that nickel plate and it's going to corrode. And they can fail even from the first day of ownership. Flat repair, somebody, most of the problems you see is somebody that can't dismount the tires properly when they have the sensors in there, and they'll snap them right off. Some of them are clogged. You've seen that happen before? Yeah, so have I. Yeah. What was that? Oh. I have another 7-minute video here.
According to the TPMS final rule established by NHTSA, the TPMS on new vehicles is required by law to operate at the first point of sale. In order to make sure that the driver will know when their tires are not being monitored, NHTSA requires the vehicle manufacturers to include a malfunction indicator, or MIL, as part of the TPMS. The MIL is designed to warn the driver that the TPMS is not operational, so they do not have a false sense of security. Even though the purpose of the MIL is to warn the consumer, it also serves as an important warning for the technician. If a technician notices a malfunction indicator after starting a customer's vehicle, stop. Do not move the vehicle until the driver has been informed that the TPMS was inoperable prior to service. There are several TPMS failure modes that can result in a malfunction indicator. Among them are sensor battery life, sensor failure, antenna failure, and TPMS power loss. In any case, technicians will need a properly formatted TPMS scan tool that can be connected to the OBD2 port under the dashboard in order to properly diagnose and repair a TPMS and eliminate a MIL on many domestic and import vehicles. The first step to diagnose a TPMS indicator light on the instrument panel is to identify the type of light that is being illuminated. If the TPMS indicator light is solid, then this is known as the low tire pressure telltale. When the telltale is illuminated, it is a warning that the air pressure in one or more of the tires has at least 25% of the required amount of air pressure in the tire. Or, in some instances, it will indicate that one or more tires are significantly overinflated. If a low tire pressure telltale is identified, the technician must check the air pressure in all tires. This can be accomplished by using an air gauge or a TPMS activation tool that displays air pressure. If one or more tires are underinflated, adjust the air pressure to the settings listed on the vehicle tire placard. In some instances, once the correct pressure is added to the tire, the telltale will go out. However, some vehicles require a system relearn following an air pressure adjustment, or need to be driven in order for the telltale to go out. Also, some Asian models utilize a tire pressure sensor in the full-size spare. If the spare tire is underinflated, the low-pressure telltale will still be illuminated, even if the 4 tires on the ground have the correct inflation pressure. If the technician confirms the inflation pressure and completes a relearn procedure, but the telltale remains illuminated, then there may be another issue that needs to be resolved. The first step toward diagnosing an unknown TPMS telltale is to use an electronic TPMS activation tool in order to see what pressure the sensor is actually transmitting. On this vehicle, the sensor was transmitting a signal that indicated the tire had about 41 psi, but the air gauge indicated the inflation pressure was 30 psi. As you can see, the sensor still reads about 41 psi outside the tire. If the reading on the activation tool is not within a few pounds of the actual inflation pressure inside the tire, as indicated by the gauge, the sensor may need to be replaced. However, if the air gauge reads the correct pressure, but the tool reads 0 psi, there could be something blocking the sensor port on the inside of the tire, which causes the telltale to illuminate. In most of these situations, the tire will need to be demounted to accurately determine the cause of the problem. It may also be necessary to view the vehicle's data stream while the vehicle is in motion in order to see how the sensor's air pressure data is being read by the vehicle's ECU. A flashing indicator light, or a yellow light with the letters TPMS, is known as a malfunction indicator light, or MIL. The MIL will flash for 60 to 90 seconds and then remain solid. When illuminated, the MIL is signaling the driver that there is a malfunction in the vehicle's TPMS, and the system is currently not monitoring air pressure. Once the MIL has been identified, the technician needs to determine the component that has the malfunction. If available, a properly formatted scan tool can be used to read the vehicle's diagnostic trouble codes, or DTCs. On this vehicle, the DTC reads, Tire Pressure System Sensors Not Learned. To fix this problem, the technician must perform a system relearn as outlined in the TPMS relearn chart. If a scan tool is not available to read the DTCs, Then the technician may be able to locate the malfunctioning component by trying to activate each sensor with a TPMS activation tool. In this example, all of the sensors appear to be functioning properly. So the next step would be to follow the relearn procedure as outlined in the TIA TPMS relearn chart. The sensors must be activated in the following order: left front, right rear, and left rear. A double horn chirp signals the end of the learn procedure. After the double horn chirp at the left rear, turn the ignition off and then back to the on position with the engine off to verify that the mill is no longer illuminated. This 2008 Toyota Camry Hybrid has a mill light on the instrument panel. A quick walk around with a TPMS activation tool shows that the left rear sensor is not transmitting and may need to be replaced. This is most likely the cause of the mill. According to the TIA TPMS relearn chart, the new sensor IDs must be registered to the vehicle using a properly formatted scan tool. Once the new sensor is installed, the technician must register all of the IDs into the vehicle's ECU. On many Toyota vehicles, once the new sensor IDs have been registered, the mill will continue to illuminate until the vehicle has heard from all of the sensors. When the mill is no longer illuminated, all of the sensors are communicating with the vehicle. If the mill goes solid, then the IDs were not properly entered into the vehicle. The sensors are not transmitting properly, or there could be a problem with the vehicle's ECU. When reprogramming new sensor IDs on a Toyota, do not press the TPMS set switch unless all of the IDs have been programmed into the vehicle's ECU. If the TPMS set switch is pressed before all of the IDs have been programmed, the technician will be locked out of the system. According to the TPMS final rule established by NHTSA, the TPMS on new vehicles is required by law to operate at the first point of sale. In order to make sure that the driver will know when their tires are not being monitored, NHTSA requires the vehicle manufacturers to include a malfunction indicator, or MIL, as part of the TPMS. The MIL is designed to warn the driver that the TPMS is not operational, so they do not have a false sense of security. Even though the purpose of the MIL is to warn the consumer, it also serves as an important warning for the technician. If a technician notices a malfunction indicator after starting a customer's vehicle, stop. Do not move the vehicle until the driver has been informed that the TPMS was inoperable prior to service. There are several TPMS failure modes that can result in a malfunction indicator. Among them are sensor battery life, sensor failure, antenna failure, and TPMS power loss. In any case, technicians will need a properly formatted TPMS scan tool that can be connected to the OBD2 port under the dashboard in order to properly diagnose and repair a TPMS and eliminate a MIL on many domestic and import vehicles. The first step to diagnose a TPMS indicator light on the instrument panel is to identify the type of light that is being illuminated. If the TPMS indicator light is solid, then this is known as the low tire pressure telltale. When the telltale is illuminated, it is a warning that the air pressure in one or more of the tires has at least 25% of the required amount of air pressure in the tire. Or, in some instances, it will indicate that one or more tires are significantly overinflated. If a low tire pressure telltale is identified, the technician must check the air pressure in all tires. This can be accomplished by using an air gauge or a TPMS activation tool that displays air pressure. If one or more tires are underinflated, adjust the air pressure to the settings listed on the vehicle tire placard. In some instances, once the correct pressure is added to the tire, the telltale will go out. However, some vehicles require a system relearn following an air pressure adjustment, or need to be driven in order for the telltale to go out. Also, some Asian models utilize a tire pressure sensor in the full-size spare. If the spare tire is underinflated, the low-pressure telltale will still be illuminated, even if the 4 tires on the ground have the correct inflation pressure. If the technician confirms the inflation pressure and completes a relearn procedure, but the telltale remains illuminated, then there may be another issue that needs to be resolved. The first step toward diagnosing an unknown TPMS telltale is to use an electronic TPMS activation tool in order to see what pressure the sensor is actually transmitting. On this vehicle, the sensor was transmitting a signal that indicated the tire had about 41 psi, but the air gauge indicated the inflation pressure was 30 psi. As you can see, the sensor still reads about 41 psi outside the tire. If the reading on the activation tool is not within a few pounds of the actual inflation pressure inside the tire, as indicated by the gauge, the sensor may need to be replaced. However, if the air gauge reads the correct pressure, but the tool reads 0 psi, there could be something blocking the sensor port on the inside of the tire, which causes the telltale to illuminate. In most of these situations, the tire will need to be demounted to accurately determine the cause of the problem. It may also be necessary to view the vehicle's data stream while the vehicle is in motion in order to see how the sensor's air pressure data is being read by the vehicle's ECU. A flashing indicator light, or a yellow light with the letters TPMS, is known as a malfunction indicator light, or MIL. The MIL will flash for 60 to 90 seconds and then remain solid. When illuminated, the MIL is signaling the driver that there is a malfunction in the vehicle's TPMS, and the system is currently not monitoring air pressure. Once the MIL has been identified, the technician needs to determine the component that has the malfunction. If available, a properly formatted scan tool can be used to read the vehicle's diagnostic trouble codes, or DTCs. On this vehicle, the DTC reads, Tire Pressure System Sensors Not Learned. To fix this problem, the technician must perform a system relearn as outlined in the TPMS relearn chart. If a scan tool is not available to read the DTCs, then the technician may be able to locate the malfunctioning component by trying to activate each sensor with a TPMS activation tool. In this example, all of the sensors appear to be functioning properly. So the next step would be to follow the relearn procedure as outlined in the TIA TPMS relearn chart. The sensors must be activated in the following order: left front, right rear, and left rear. A double horn chirp signals the end of the learn procedure. After the double horn chirp at the left rear, turn the ignition off and then back to the on position with the engine off to verify that the MIL is no longer illuminated. This 2008 Toyota Camry Hybrid has a MIL light on the instrument panel. A quick walk around with a TPMS activation tool shows that the left rear sensor is not transmitting and may need to be replaced. This is most likely the cause of the MIL. According to the TIA TPMS relearn chart, the new sensor IDs must be registered to the vehicle using a properly formatted scan tool. Once the new sensor is installed, the technician must register all of the IDs into the vehicle's ECU. On many Toyota vehicles, once the new sensor IDs have been registered, the MIL will continue to illuminate until the vehicle has heard from all of the sensors. When the MIL is no longer illuminated, all of the sensors are communicating with the vehicle. If the MIL goes solid, then the IDs were not properly entered into the vehicle. The sensors are not transmitting properly, or there could be a problem with the vehicle's ECU. When reprogramming new sensor IDs on a Toyota, do not press the TPMS set switch unless all of the IDs have been programmed into the vehicle's ECU. If the TPMS set switch is pressed before all of the IDs have been programmed, the technician will be locked out of the system.
It's extremely important to remember that you got the 25% threshold from the OE placard, not from what was put on aftermarket. And placard pressure, I think we all know what cold pressure is when that's being taken. Here's an example of all the scan tools, not all of them, but many of them that are on the market right now that will all activate domestic TPMS. All domestic. If you want to include the foreign, particularly the Asian, you need a tool with an OBD2 plug. That's the Bartec 400, the ATEC VT55. Snap-on has now come out with the TPMS 3, which is just like the VT55. That will work for all of the Asian vehicles. The Genesis Evo system, diagnostic tool that has the TPR tool with it, that will also work. That's very expensive. That's probably $3,000 for the whole diagnostic kit and everything. But then that does everything. Does your DTC codes and everything. The TIPS tool here and the Snap-on, there's an LF trigger on this end and a magnet on the other. If you want to use the Fords that use the magnet. But most of the Fords from 2008 on, even if they have a magnet triggered sensor, will also respond to an LF trigger. The GMs that require a deflating to trigger it will also work with a scan tool. That'll save you time. You don't have to reinflate the tires when you're done. Just hit it with a scan tool, the horn chirps, away you go. If that looks familiar, it is. Different scan tools will activate the sensor, they record the ID, they read the sensor transmissions, and like I said, some vehicles require the use of a cable in the OBD2 to upload the IDs in a relearn. The ATEC VT55 will hold the information on the screen until you go to the next tire. The Bartec will show it on the screen, bless you, will show it on the screen for a matter of seconds, and then it automatically goes to the next tire. So one of the reasons I prefer one over the other. I have a 29-minute video. It goes through every relearn procedure. I think it will be beneficial to all of you. It's also warm in here. If you want to get up and get a soda or something to drink, now's a good time until I get this video started. Have so many different relearn procedures, even within the models. It's mind-boggling. And I hope that this presentation, because I don't know what vehicles you're working on, it could be all of them, it could be some of them, but it's important to know that you really need to check the relearn procedure in the owner's manual to make sure you're following the right one. These are the companies that supply OE sensors. VDO was owned by Siemens up until 2008. They sold us to Continental. And so now you'll see some sensors that have Siemens VDO and some of them will have Continental. TRW makes OEs, Lear, Schrader. Baru is mainly European, and Pacific. Out of these, the multi-application or aftermarket sensors, Ready Sensors made by Continental, VDO. Easy Sensor is Schrader. They all have their advantages and disadvantages. I happen to think that the Easy Sensor is better. Orange is in the mix here. I think Standard Motor Products handles them. They don't do any OE work, so I would be leery. The folks that manufacture the OEs, we also manufacture the receivers. Continental knows how this system works. If you're not into TPMS yet and you want to, just battery life alone is going to start to hit. We're figuring 64 million batteries or sensors need to be changed by 2014. Of course, Ready Sensor, we've designed, manufactured, and supplied direct TPMS for the OEMs. We began developing it in 1998. We've been an OE supplier in North America since 2003, and we began the aftermarket 2005. They have the form, fit, and function that's the exact same components for the OEs as in the aftermarket. These are our OE customers worldwide. Every one of these vehicles has some VDO part in it somewhere. And TPMS right now, it's mandated by law. We can't get away from it. As much as some of you may like to, it's here to stay. Again, I want to emphasize these repair kits, using the right ones, changing them every time you change a sensor. You might have noticed we work closely with TIA. They supplied us with this chart. I'm going to skip through tire pressure monitoring pretty quick here. I think everyone knows the basics. The interesting thing here is that only 15% of the drivers now properly check proper tire inflation. We all are in the habit of walking around and checking our tires. Most people don't. I was in this 55% until several years ago. 55% wrongly believe that the correct inflation pressure is printed on the tire sidewall. No, that's the maximum load pressure. And a third of drivers wrongly believe that if they're taking a trip with a fully loaded vehicle, that they are better off if their tires are a little bit underinflated. I never heard that one before. I've never done that. Improper tire inflation is just a cause for a whole lot of problems. It's the only thing that connects the vehicle to the highway. And the whole thing that started this was, remember, the rollover, Firestone tire on a Ford Explorer. That's what got the attention of all of this regulation. If you want to know the formula or the math involved in pressure behavior, I'll be glad to go over it. It's pretty simple. When the temperature goes up, so does the pressure. When the temperature goes down, the pressure goes down. And it's also seasonal. It goes through a season, it goes through day-to-day operation, and it goes changes while you're driving as well. It'll even, over the length of the time, lose tire pressure. I had a class yesterday, we were debating nitrogen versus regular air. I don't know. 70% of what we have right now, or what we're breathing right now, is nitrogen. Some chemist told me the nitrogen molecules are larger and they won't leak through the tires. It could be true. I don't know. It doesn't affect the sensor whatsoever. If you like pure nitrogen, go ahead. So they put this in a graph, and when you get down into this area right here, it's what we call the Christmas tree effect. The light's gone on, the light goes off. Light goes on, light goes off. You're right on the threshold of that 25%. And on that line, some of the OEs in their protocol, it could be closer or a lot closer than the 25%. It could go on within 3 or 4 pounds. And you may have seen that. So they're starting to get a light on and off, maybe just 2 or 3 more pounds in the tire and it's done. Always check the spare too. A lot of people overlook the spare. If it's a full-size spare with a sensor in it, it could be triggering it. Most drivers lack awareness and understanding of the loading information or the vehicle placard. We've all seen that. 2001 Volvo S60 took me about 5 to 6 minutes to find it. You know where it is? The inside of the fuel door. Made sense to me. I'm looking on door jambs, I'm under the hood, I'm in the trunk. Never thought to look in the fuel door, but that's where it is. Most drivers lack awareness of the cold inflation pressure. I'll go over this if you want. Everything on the sidewall of the tire means something. It's mandated by law to be there. Tire sizes. I do this for some of the VOTEC classes. I think we all understand the meaning of all the numbers and where they are for the tire sizes. Section width, aspect ratio, all that stuff. Rim diameter. So the importance of tire pressure reached a point where the federal government mandated tire pressure monitoring with and that was the Ford Explorer. So in Europe, every 7,000 kilometers, they had a flat tire. The whole issue behind this, the number one reason for TPMS is safety, period. And right now, it's the law. The one video talked about the Federal Motor Vehicle Safety Standard. That dictates what's in the owner's manual. It also says that the driver must be warned within 20 minutes. It's an awfully long time, but that's what the government says. This section covers TPMS malfunction and covers what needs to be written in the owner's manual. Again, steady light, most likely just pressure somewhere. When you first turn the ignition on, it's flashing and then goes steady, you have a communication issue. Now you need to find it, do some troubleshooting, find out where it is. And this is on all vehicles built after September 1st, 2007. Tire pressure monitoring is now mandated and cannot knowingly be disabled by an OEM or aftermarket service provider. Just so you know that. A lot of people in this area of the country, particularly in the Northeast, summer and winter tires. They don't want to spring for another set of sensors. Just throw them on, I don't care if the light's lit. If that vehicle comes into your shop with the light out, it has to leave with the light out. If it leaves with the light on, legally, technically, you're liable. This is a little history of the sensors starting in 2001. Went from fixed to angled valve stems. Then we had the banded. Now we're moving to the snap-in, the rubber snap-in. Service requirements.
In order to fulfill the federal requirements for monitoring tire pressure, manufacturers have to position an RF sensor inside the tire and wheel assembly. The most common frequencies used by vehicle manufacturers today are either 315 MHz or 433 MHz. While TPMS activation tools can be used to identify the signal, the frequency may or may not be imprinted on the body of the sensor. As a result, technicians cannot always determine the frequency based on the physical look. One manufacturer changes the color of the plastic housing, using dark gray to indicate a 433 MHz sensor and light gray for a 315 MHz sensor. Unfortunately, technicians cannot apply this rule to other manufacturers, as the various colors and profiles may transmit at different frequencies with different protocols. In fact, when General Motors introduces a global RF protocol of 314.9 MHz for all vehicles starting in 2011, there will still be differences depending on the model. Since the vehicle is engineered to only receive one RF signal to monitor tire pressure, the sensor must transmit using the same frequency and protocol, which means two sensors can be physically identical and transmit at the same frequency, yet the protocols are completely different, so they will not communicate with the vehicle. That's why every TPMS sensor includes an identification number, so it can be cross-referenced with the vehicle manufacturer to ensure the frequency and protocols are the same. In order to make this process easier, TIA created a TPMS relearn chart that includes the sensor part numbers for the most popular aftermarket sensor and service pack manufacturers. The chart is divided into blue for domestic vehicles and red for imports. It is also organized alphabetically by vehicle manufacturer and then model, so technicians can easily access the information. With access to this information, technicians can easily service the various types of TPMS sensors. One of the most popular TPMS sensors is the aluminum one-piece clamp-in assembly. In many cases, it has a fixed angle that fits most original equipment and aftermarket rims. When servicing a one-piece clamp-in valve stem sensor, the first step is to select the correct socket and remove the hex nut on the outside of the rim. Most hex nuts require an 11mm or 12mm socket. If corrosion is visible or the hex nut shows unusual resistance, notify the customer that the sensor may need to be replaced in order to service the assembly. After the hex nut is removed, it should be immediately discarded so it cannot be reinstalled. Likewise, the rubber seal or grommet must be replaced whenever the sensor is removed from the rim for any reason. Special tools are available to make this process easier without any risk of damaging the sensor or creating a sharp edge that may cause additional damage. The next step is to remove any foreign material from the valve stem so the threads can be inspected. If worn or damaged threads are found, then the sensor must be replaced. Technicians should also clean the valve hole in the rim and inspect it for any damage or evidence of corrosion. Once the sensor and valve hole appear to be in good condition, technicians must consult the manufacturer to select the proper hex nut and grommet, which is also referred to as a service pack. After determining the year, make, and model of the vehicle, technicians can find the correct part numbers by searching the manufacturers, which are arranged in alphabetical order. Let's say the part numbers are needed for a 2010 Chevrolet Colorado. The technician should use the blue domestic side and locate Chevrolet and then the light truck SUV section. Once again, the model names are arranged alphabetically, so Colorado can be quickly found in the first column on the left. The second column indicates the year, which in this case is 2006 to 2010. The column marked Sensor Manufacturer shows the original equipment sensor, which is Schrader. The original equipment part number for the sensor, 15122-618, is in the next column, while the Schrader part number for the same sensor is 20131. The Schrader service pack number for this sensor is 20006. Each of the remaining columns on the chart show the aftermarket sensor and service pack part numbers for popular suppliers. As long as the replacement components are selected from the part numbers on the same line for the 2006-2010 Chevrolet Colorado, they are interchangeable. However, if the chart indicates two different fitments, then all of the components may not be interchangeable. For example, if the vehicle was a 2008 Chevrolet Malibu, then it may have clamp-in or snap-in sensors. If it has clamp-in sensors, then there are two different types of sensor that may be on the vehicle, one from Siemens and one from Schrader. As you can see, the service pack numbers for each of the manufacturers are different, so technicians must make sure they verify the type of sensor they're working with before selecting the correct hex nut and rubber grommet. Once the proper parts have been selected, slide the rubber grommet over the valve stem and make sure it is fully seated at the base. A special tool can be used to assist this process. Next, position the sensor in the valve hole and then hand tighten the hex nut until the sensor is snug. Like most aspects of TPMS service, the torque specification for the hex nut is also manufacturer specific. So in the case of the 2008 Chevrolet Malibu, the installation torque would be 62 inch-pounds for a Schrader sensor or 80 inch-pounds for a Siemens assembly. The number in parentheses refers to the torque in Newton meters, which is 7 Newton meters for the Schrader and 9 Newton meters for the Siemens. Select the correct socket and then adjust the torque wrench to the proper setting for the sensor. Slowly tighten the hex nut, holding the end of the torque wrench until the handle breaks slightly to indicate the proper torque has been established. Do not use a torque wrench like a ratchet because it's easy to miss the slight handle break and over-torque the hex nut. The other type of one-piece sensor has an adjustable valve stem that can accommodate various valve hole profiles. This particular sensor has a metal band that acts as a link between the electronics in the sensor and the valve stem that acts as an antenna. The service procedures for a one-piece adjustable valve stem sensor are identical to the fixed angle, with the exception that the sensor may need to be adjusted so it is clear of the bead seat on the rim. Another trait that is shared by every aluminum clamp-in valve stem sensor is the special nickel-plated valve core. The nickel plating covers the brass and prevents corrosion in the valve stem. That's why valve core torque is so important when servicing a clamp-in sensor. Over-torquing the core can expose the brass and cause the core to become seized in the valve stem. If the valve core in an aluminum clamp-in sensor is difficult to remove, technicians should deflate the tire by depressing the valve core and then advise the customer to purchase a new sensor. Likewise, if a chrome, metal, or custom valve cap is difficult to remove, technicians should immediately notify the driver that in order to deflate and then reinflate the tire, the valve stem sensor will need to be replaced. Aluminum clamp-in valve stem sensors require hardened plastic valve caps that include a rubber O-ring seal at the base. As a rule, most service packs also include a new nickel-plated valve core and self-sealing valve cap, so technicians can replace all of the critical components. The two-piece clamp-in valve stem sensor consists of two separate parts, the sensor and the valve stem. The sensor houses the electronics that measure the inflation pressure inside the tire and relay the data to the vehicle with an RF signal, while the valve stem is used to inflate and deflate the tire, as well as attach the sensor to the rim. Removal is identical to the one-piece clamp-in sensor, so the hex nut must be removed with an 11 or 12 millimeter wrench and socket. Once the sensor is removed, immediately discard the hex nut, any spacers or washers, and the rubber seal or grommet. Many German automobiles use a two-piece clamp-in valve stem sensor manufactured by Baru. The Baru system uses a self-locking torque screw to attach the sensor to the valve stem. Baru has 4 different valve stems, each with a different length to accommodate all types of rims: silver, green, black, and orange. When replacing the valve stem on a Baru sensor, always use the correct part number or color to ensure the sensor is properly positioned on the rim. Baru also uses 2 different spacer rings, beveled and flat. The beveled spacer ring has a 45-degree bevel and is required for the beveled valve hole on original equipment rims from Mercedes-Benz and Audi. The flat spacer ring does not have a bevel and should be used on rims with a flat valve hole, like BMW. After the correct components have been selected, position the valve stem in the valve hole so the small hole is facing out, and then hand tighten the hex nut until the assembly is snug in the hole. Place the positioning pin in the hole on the valve stem and then torque the hex nut to 35 inch-pounds or 4 Newton meters. Remove the positioning pin and then lightly press the sensor against the rim before torquing the torque screw to 35 inch-pounds or 4 Newton meters. Another type of two-piece clamp-in sensor uses a special screw with a square collar that fits into a slot to secure the valve stem to the sensor. After the screw is properly positioned in the slot, hold it in place and turn the valve stem 3 to 4 full turns. The screw should be completely in the slot, and the valve stem should still be loose and able to move the full length of the slot. Position the sensor in the valve hole and then hand tighten the hex nut until the assembly is snug. These sensors may include a special hex nut that has a breakaway flange that will break at approximately 20 inch-pounds or 2 Newton-meters. After the flange has been broken, the hex nut should be tightened to 35 inch-pounds or 4 Newton-meters. Another two-piece assembly consists of a sensor and a valve stem, but the stem itself holds the pieces together. The valve stem slides into the sensor body, so the flat edges are aligned in the channel. A large spacer cup fits over the valve stem with the lines together so it is secure. The grommet is positioned at the base to temporarily hold it together. The valve stem should still be loose and the marks aligned before the sensor is installed on the rim. On most two-piece clamp-in sensors, technicians must make sure the sensor is positioned against the rim and is clear of the bead seat. When removing a two-piece rubber snap-in valve stem sensor, the best practice is to remove the sensor and then carefully use a sharp knife to trim away the rubber so the valve stem can be removed from the rim. Do not attempt to remove a two-piece rubber snap-in valve stem sensor from the outside using a standard valve stem remover with the sensor still attached. The service pack for a rubber snap-in valve stem sensor includes a new self-tapping torque screw that actually cuts the threads in the bottom of the replacement stem. Technicians should torque the torque screw up to 11.5 inch-pounds and then make sure the sensor is held tightly against the valve stem. Apply an approved rubber lubricant to the valve stem and then install the sensor using a standard rubber snap-in valve stem installation tool. Band-mounted sensors do not require regular maintenance since they are not part of the valve stem assembly. In order to replace a band-mounted sensor, technicians must first remove the retaining clip opposite the hinge end of the cradle. After the clip is removed, the sensor can be removed from the cradle. When replacing the band, the first step is to clean the area of the drop center opposite the valve stem. Next, remove the cover on the adhesive tape on the back of the cradle and press it on the drop center of the rim so the edge is parallel to the outside rim flange. Then thread the band through the slots in the cradle to secure it to the rim and begin tightening the screw on the worm gear. After the recommended torque of 27 inch-pounds or 3 Newton-meters has been reached, technicians should trim the excess band outside the worm gear. The new sensor fits under the hinge, so the retaining clip can be installed, which secures the sensor to the cradle.